So the last test we're going to do here is called the ratio test, and I just printed this all on there so that you have it. As a heads up, this one is a little bit of writing, but it's not necessarily hard, but I suggest not skipping steps unless you really feel comfortable skipping steps in your head, just to make sure that you don't lose track of what you're doing, because it's going to look kind of like the alphabet threw up on your paper, okay? So you're going to do this limit as n goes to infinity, a sub n plus 1, so you just plug in n plus 1 everywhere you see an n, over a sub n, that's just the series itself. If that comes out smaller than 1, it converges. Bigger than 1 or goes to take 2. Bigger than 1 or goes to infinity, it diverges. And if it equals 1, then bummer, it's no conclusion, and you have to pick one of these other things to get through it. Okay. Before we get started, I just want to review like limits and where things go real quick. Oh, question. It always makes me nervous when there's a question before I did anything, but let's see how this goes. Go ahead.
The limit sign backwards.
Oh, yeah, the arrows are going the wrong way. I apologize. That's super tiny. I didn't even catch that. Yes, its limit as n goes to infinity. I'm sorry. I'm very sorry. An exponential is going to grow faster than a polynomial, which grows faster than a logarithmic. And that's like the who's in charge here thing when you're going to infinity. And I'm going to add a fourth one in there, which is that factorial. The factorial grows even faster than an exponential. So if it's a battle of which one's growing faster, the factorial is going to grow faster than any of the other ones. Cool? Okay, so that's like the order. Like this beats this, which beats this, which beats this. Here we go. You're going to write limit n goes to infinity. All right, we're going to draw a big absolute value. Now, with staying organized here, and again, you can write however you write, but here's my suggestion, because you're going to get a fraction over another fraction. I make the middle fraction bar touch the absolute value, if that makes sense. Like, so I can tell which fraction bar goes with which fraction. You'll see what I mean in a second. Oh, okay, good. Thank you for coming with me on that, because otherwise you have the absolute value bars, and then you're going to have all these other fraction bars, and it's going to look awful. This isn't hard. It just looks really awful. So we're going to plug in n plus 1. So you're going to have 2 to the n plus 1 over n plus 1 factorial. I just plugged n plus 1 in for n. And then that goes over the series itself. So 2 to the n over n factorial. And what's always going to happen is that when you divide by a fraction, you multiply by. And so once we do enough of these, you might start skipping this step. I never do. I always write it out, but it's going to turn out the same way every time. You're always going to flip the denominator. So it's going to be limit n goes to infinity, giant absolute value. On the top, you're going to have 2 to the n plus 1. And then because this is going to flip, this n factorial is going to come up to the top. And then on the bottom, you're going to have basically the middle stuff. That's the other way I kind of think of it, is like this. Do you see how this stuff in the middle is going to be what goes on the bottom? You want to line them up though. So I'm going to put the 2 to the n underneath the 2 to the n plus 1. Like you want to kind of match them with what they go with. Because in the next step, and these always turn out the same way, you're going to get stuff that cancels out. Like there's going to be this canceling out step. So let's see what we can get to cancel out here. If you have 2 to the n plus 1 over 2 to the n, here's what's happening. In the numerator, you have 2 times 2 times 2 times 2 times 2 times 2, n plus 1 times. In the denominator, you have 2 times 2 times 2 times 2 times 2 times 2, n times. Are you following me here? Imagine like a list of 2's and another list of 2's. All the 2's are going to cancel except one of them, and it's going to be on the numerator. Do you see what I'm saying? You're going to have 1, 2 left over there. Now, the same thing is going to happen with these factorials. You're going to have an n plus 1 left in the denominator. I don't want to write all over this paper, so let me just grab a scratch sheet of paper to show you. Do you remember how a factorial works? How does a factorial work? Like if you did 4 factorial, it would be what? Okay, so like if you have n factorial, it's n, and then you'd have, well, you know what, let me use an actual number. If you had 4 times 3 times 2 times 1, but on the denominator, it was 1 higher than that. Do you see how like these all cancel and all you're left with is like that? Like visually, that's what's happening then. Okay. And with the 2s, it was like this, but in the denominator, like you had 1 extra one, or I guess it was in the numerator. I wrote it the wrong way around. Anyway, they're all canceling except one of them. And that you're going to get used to this because it's going to happen every time. All right, here's the point. As n goes to infinity, where does this limit go? 0. And here's the big question. Is that bigger or smaller than 1? That's what tells you if it converges or diverges. Smaller than 1. So 0 is less than 1. Converges. And you would normally say converges by ratio test. All we're doing here today is the ratio test. So I'm fine with you just saying converges. We're just going to practice that a couple more times. But they turn out the same way. You set it up. Then you're going to, reciprocate. Stuff's going to cancel. You're going to do the limit and then see if it's bigger than smaller. Those are how the steps go every time. Okay. So let's try another one. They can sometimes look rather complicated. You just have to stay organized. Right. So draw a big absolute value. And again, my recommendation is make the middle fraction bar touch the absolute values because then you can really kind of separate what's what. So we're going to plug in n plus 1. It's n plus 1 squared. 2. Oh, this would be 2 to the what? If you plug in n plus 1, it would actually be n plus 2 because it's n plus 1 plus 1. So n plus 2. And then over 3 to the n plus 1. And on the bottom, you're just going to copy that over. It's just all the same stuff. So again, it kind of looks awful. But just remember, a good bit of that's going to cancel. So you just kind of have to trust the process and keep going. So in the numerator, we're going to have n plus 1 squared. And then this 2 to the n plus 2. And then what else? What's going to go up there? Because this is going to flip. Yeah, the 3 to the n is going to go up there. And then on the bottom is all the stuff in the middle. That's usually how I remember that. It's all this stuff. But you want to line it up so that it makes sense. So what would you put first? Like first we would put I would put the n squared first, like I'm lining these up. And then what would you put next? Like you want to line what up with this one? Yeah, 2 to the n plus 1, and then you would do 3 to the n plus 1. So now we're going to see what cancels. I realize it looks awful. I know you're like, we hate this. This you really can't do anything with. So I'm going to leave that for a second. The n plus 1 squared and the n squared, there's really not much you can do with that. Let's look at the 2s and the 3s. You're going to have 1, 2 left over. Where's it going to go? On the numerator or the denominator? On the top. Okay, so we're going to have a 2 up there. And you're going to have 1, 3 left over, which is going to go... I heard some disagreement there. It's going to go on the bottom. All right. And then you have the n plus 1 squared and the n squared that you really kind of can't do anything with. And then you evaluate the limit. So again, it's like you set it up, you reciprocate, you get stuff to cancel out. Now we're going to do the limit. This would be an n squared if you were to like expand that out. This is also an n squared. So when they're the same, you use what? Yeah. So your limit comes out to 2/3. I guess I can like barely fit that in there. And the whole point is 2/3 bigger or smaller than 1? So 2/3 is smaller than 1, and that means converges. And again, if your problems are all mixed up, you would have to say converges by ratio test, but we're just doing the ratio test. I'm going to change the next problem because I was looking back at this, and that problem is just awful. And I am not trying to torture you. So if you could just scribble that one out, I'm going to give us a little bit of a nicer one. I was looking back at that and I'm like, I cannot believe I made my class do this problem. That one's just like completely horrible. I guess I was mean last year. I'll be a little nicer to you guys. right, so we're gonna do limit n goes to infinity, and then we're gonna plug in n plus 1. That's what'll go on the top. So you'll have n plus 1 factorial over 5 to the n plus 1. So it's the series, but just plug in n plus 1. And then on the bottom, you just copy that over.
Yeah.
Okay. All right, and now we're going to flip this over. So on the top, you're going to have the n plus 1 factorial. And what else? What else is going to flip up to the numerator? Like, what other part is going to go here? Yeah, the 5 to the n. And then all this stuff in the middle is what goes on the bottom. But you want to line it up, like make them line up with the things they're going to cancel with. So what would we write first? Yeah, n factorial, like n. And then your 5 to the n plus 1. And now we're going to cancel stuff out. So looking at the factorials, what's left and where does it go? Good, n plus 1 will be on the top. And then for the 5s, there's 1 5 left, which will go on the bottom. And then you evaluate the limit. So as n goes to infinity, this numerator is going to get bigger and bigger and bigger and bigger. So this goes to infinity. And so your conclusion is diverges by ratio test. We have time to do 2 more. We'll finish it, I promise. All right, so we're going to do limit n goes to infinity. Now, because there's going to be an absolute value, I can leave off this part. Do you see what I'm saying? It's going to all be positive, so you can basically ignore that. We're going to plug in n plus 1. So that would make this an n plus 2. And then on the bottom, just copy the series. And then we're going to reciprocate. So it'll be square root n plus 1. And then what else is going to go on the numerator? Like it's going to flip. So what else is going to go up there? Yeah, the n plus 1. I'm going to just put parentheses around that. All this stuff in the middle is going to go on the bottom, but you want to line it up. So put the square root of n first, and then the n plus 2. Now, nothing is going to cancel there, unfortunately. So we can just go ahead and evaluate the limit. So let me walk you through this. Just watch what I'm pointing to. You have an n times the square root of n. This is n to the 1. This is n to the 1/2. So that'd be 1 1/2 or 3/2. Down here, do you see how it's the same thing? You have an n to the 1 and an n to the 1/2, n to the 1 1/2. So since they're the same, you would use what? Coefficients. Now nothing's written, which means they're both 1, and so this comes out to 1. Flip back to the other side. Unfortunately, what does that mean? It means that there is a no conclusion. It means you have to figure out something else to do. You probably wouldn't have done a ratio test with this problem in the first place. I just did it to show you what would happen if there was a no conclusion. If you looked at this problem, you would probably not have done this. What test would you do? You would do an alternating series test. You wouldn't even go through this. I'm just showing you what it would look like if it came out to a no conclusion. Okay, let's do an alternating series test. That would be limit as n goes to infinity of the series. Now we need for it to be 0. You just have to check. Will that actually come out to 0? Yes, denominator has a higher power than the numerator. The denominator is growing faster, so it's going to come out to 0. And then you have to show that the terms are getting smaller and smaller. So if you plug in n plus 1, that has to be smaller than the series. And then we check if that's true, and it is. Sometimes I'll plug in 1, plug in 2, plug in 3 and see what happens. But for the sake of time here, this is going to be true for n's bigger than 1. And so we would say converges by alternating series test. So if you get a no conclusion, you have to go back to the drawing board and figure out something else. But in this case, you probably wouldn't have done a ratio test anyway. If you see that it's alternating, you would have just done an alternating series test in the first place. I just wanted to show you what that looked like if it came out to 1. All right, we're just going to try one more. Limit n goes to infinity, gigantic absolute value. So when you plug in n plus 1, what is that going to give you up here? N plus 3 over n plus 1 factorial. And then on the bottom, it's just recopying what's there. And again, if you get to the point where you feel comfortable skipping this step and you can just go ahead and flip it in your mind, you can do that. I never do. I always write it out because I just have to stay organized like that. So in the numerator, you'd have the n plus 3 and what else? N factorial. And are you guys starting to see how they turn out the same every time? This looks awful, but I actually don't mind the ratio test. It's not too bad because you do the same thing for all of them. All right, and then this middle stuff is going to go on the bottom. I'm going to put the n plus 2 first, and then the n plus 1 factorial. And then we can try to cancel. Not much is going to cancel out, but the factorials will a little bit. So the n plus 3 and the n plus 2 are going to unfortunately just stay. There's nothing we can do with that. But when you look at the factorials, like if you were to write it all out, it's all going to cancel except for what? N plus 1, and it'll go right there. And then you evaluate the limit. So in the numerator, you have an n. And the denominator, if you multiplied these, you would have an n squared. So since the denominator is growing faster, this goes to 0. And then what's the big conclusion? Converges because 0 is less than 1.